that we have with the vagus nerve. So neuroprotection. We have done dozens of studies, I think about 50 or so trials, large trials, multi-center trials, and every single one of them have failed. This has been a really challenging task for us. And part of it is that because many of these trials were observational, part of it is that many of these trials were looking for outcome measure that we don't have right now, the precise outcome measure to say Parkinson's disease has slowed down. We don't have a really good marker for Parkinson's disease. We don't have a diagnostic test for Parkinson's disease. So this is just a list of these trials. Look at the number of patients that have participated in these trials. And this is 1, and then 2, and then 3. And this is not even the comprehensive list, but you can already see that there are 5,000 or more patients already studied in these trials, in very, very well-designed trials, very expensive trials, and all of them have failed. And more recently, the 2 trials we were participating in have also failed, the inosine, the uric acid one that I mentioned earlier. So what's going on in the cell? So now coming down to the actual science of the disease to see why we can or how can we solve this. So this is a cell structure, and one of the key component highlighted here is what we call mitochondria. Mitochondria are the power plants of the cell. Their job is to produce the electricity which is needed for the rest of the cell to do all the function. And one of the key abnormalities now we have fully described in Parkinson is the damaged mitochondria, that these power plants inside the cells are dysfunctioning and are not able to produce enough electricity and are slowly killed or removed, and so the cell lost power. And once the cell lost power, shutdowns happen, then other functions like cleaning system and trash collection and other things start breaking down in the result of that. So we have many mechanisms of mitochondrial damage explained now that are being targeted by the drugs. One of the central role that we have been learning is calcium. One of the study that Dr. Bertoni was part of in a consortium that is coming close now called Steady PD looked at reducing the calcium going into the cell as a mechanism of cell protection. This is one of the studies that's based on an actual cellular mechanism. So what calcium does, this is a study from a fish protein. So what calcium does is that it helps the conversion of these soluble proteins, which we call alpha-synuclein, into these large clumps that we call Lewy bodies. So the Lewy bodies are clumps of protein. That protein is normally present in the brain cells, and that Lewy body is formed by clumping of that protein. That clumping is abnormal, and if we can prevent that clumping, then maybe we can prevent the formation of Lewy bodies. So this one study looked at a protein that is present in fish from the water, fish cells, and that protein actively inhibits the clumping of the Lewy bodies into alpha-synuclein into Lewy bodies. But the problem is that that protein function is lost if there is too much calcium in the cell. And maybe that explains why we designed this trial to look at decreasing the amount of calcium inside the cell so that we can slow down the formation of Lewy body and slow down the death of cell. But that gives us another target now that protein, that parvalbumin from fish, can now be used to probably create products to stop the accumulation at a high level so that it competes with the calcium presence. So this is the calcium influx study, Steady PD3, that we were part of. Dr. Bertoni was leading it, and it looked at reducing that influx. Another function where calcium is abnormal is that there is a calcium regulating mechanism inside the cell that regulates how much calcium is present. And the one of the problem is that this calcium pump that is in the walls of those what we call endoplasmic reticulum, the area within the cell that is regulating the calcium levels, have a dysfunction because of accumulation of these alpha-synuclein. So it's a feedback mechanism. Once we have more alpha-synuclein to form more Lewy bodies, it's dysregulating the calcium pump. So there's more calcium inside, and more calcium inside is now causing the clumping, further clumping of the alpha-synuclein into Lewy bodies. So we can try to add proteins that block the clumping. We can slow down the influx of calcium inside, and we can target this particular pump, this particular enzyme within the cell wall by a targeted therapy. And there is a therapy that exists. These pumps and these kind of cellular mechanisms have been known for a while, and there are drugs that are available already in the labs to try to stop this calcium influx. So one of that chemical is cyclopizanoic acid. which is that calcium pump inhibitor, just to give you an example of translational medicine. So they took the cyclopentanoic acid, they took these worms that you're seeing, created them so that, genetically modified them, so that they start forming a lot of alpha-synuclein and start forming Lewy bodies. They then treated these worms with the cyclopentanoic acid, and they showed a reduction in the accumulation of the Lewy bodies. So the proof of concept was given in the worms already, and I'm sure now it's being translated into the higher primate models like mouse or monkey models, and then gradually will reach a human experiment, either that drug or a new drug based on the similar mechanism. Another, we are going to lengths to try to figure out how the cellular mechanism worked. So this picture is interesting because last year there was these astronauts who took the alpha-synuclein proteins into the space to see if there is no gravity present, if the binding or accumulation of these alpha-synuclein to Lewy bodies is any different than what happens on the Earth on gravity. And there was no difference. It does the same mechanism, same behaviors up in the space without any gravity. So it failed, but it shows you that what lengths we are going to try to find that cellular mechanism that explains what is causing Parkinson's. So this is a scan that you may have heard before. This is a dopamine scan, which causes a loss of dopamine, or DAT scan. What DAT scan is looking at, those highlighted yellow or orange pictures that are normal, healthy, large size on the picture on the left, and they're small in the abnormal side, is looking at this structure in the brain which is called the putamen or striatum, putamen encoded. These putamens have these special cells that are called interneurons, which are basically connecting all the other neurons. So it has all these connections, and this is where the dopamine is actually being released to do the normal function, and the loss of dopamine release in these interneurons is where the problem happens. Why I'm explaining these interneurons? Because there was this study that showed recently that these interneurons have a component of them, a portion of these interneurons, which has a dual nature. Duality. They can be stimulating or they can be inhibiting, and they shift their duality based on what input is coming to them through a chemical release mechanism of neurotransmitter. One abnormality in Parkinson's disease, because of loss of dopaminergic neurons or dopamine, is that these cells start losing their duality. They become predominantly negative. So they lose the positive side of them, and they start hating everybody, and they start becoming very negative. And again, that's a drug target where they showed that use of a known drug that already on the market called Bumetanide, which is a chloride channel inhibitor, reducing the chloride influx into these cells, reversed that loss of duality, so that cells became dual again. They became both positive and negative again. This is very interesting. Why? Because Bumetanide is already in the market, and not only that, if we go and do a literature search, somebody in 1994 reported use of Bumetanide on his 4 patients. So as a clinician, he has an observation. He was using Bumetanide, probably his own hypertensive patient. It's a diuretic medication. And he noticed that his Parkinson's patients were doing better if they were on Bumetanide. So he reported experience of 4 cases, 4 patients that he had put on Bumetanide, and they were doing better. And back in 94, he said, oh, maybe it's a good idea to use Bumetanide, but he couldn't explain why. So that was left at that. There has never been any paper after that, but now we know the science behind why Bumetanide might be useful in the brain, that cellular mechanism that explains this. Another important role is expansion beyond just these dopamine neurons. There is a growing science to show that the abnormalities in the brain of Parkinson's patient are not just limited to the dopamine neurons or even the neurons themselves. This is a type of brain cell. It's a supportive cell. It's not a neuron. It does any neuronal function. It's called an astrocyte. Astro means star-like. So this star-like cell basically supports all the other neurons functioning around it. Its job is to give them some support. It has become very significant because these astrocytes have become the center of the science of aging in the brain. That these astrocytes have what is called senescence signal, meaning aging signal, and at a certain point they turn on those signals to say, I have aged. I am an old cell. I don't need to work for too long, and that leads to death of that cell, and that leads to death of the neurons around it. So this science of senescence is becoming very important, and it's important and relevant in Parkinson's because there is a rapid or advanced or faster than normal senescence of these astrocytes in Parkinson's brain. So Parkinson's brain astrocytes, or supportive cells, are dying faster than the normal aging mechanism. And there are known drugs that could stop or reverse that aging signal. It can go to astrocytes and say, no, 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 you're not that old. Let's convert it. 60s is the new 40s. You're fine. You'll be okay. Let's reverse it. And they can start making those cells last longer. And that is another target for our therapy. And lastly, one big, huge area, just like cancer treatment that you'll be hearing in the news, is the immune therapy for Parkinson's. There's a lot of different immune mechanisms involved in Parkinson's disease that are being targeted. Let me just give you some example. There are 2 vaccines under study right now, mostly in UK, looking at vaccination against alpha-synuclein, so the body immune system gets activated against that Lewy bodies or alpha-synuclein to start clearing that out. There was first in human report of this anti-alpha-synuclein monoclonal monoclonal antibody that was published, and that trials are now going into phase 2. This was done in Europe. The phase 2 of anti-synuclein antibody is now being done in US, and we are looking to apply to be a site for that study to look at giving those alpha-synuclein antibodies to try to block the alpha-synuclein growth and promotion. Pasadena company is the prasinezumab is the drug that we will be hoping to apply for to be a phase 2 site in Omaha for this study. And there are many other immune therapies being worked by. So these chemicals don't even have a name right now, they have numbers, but you can see the list of companies that are working on these immune therapy targets for alpha-synuclein. Another immune therapy based treatment that we did or is going on that we are partly involved with is called Nilo PD. Nilo PD is looking at this mechanism that was originally discovered in cancer, in CML, chronic myeloid leukemia, where there is an overactivation of a particular enzyme inside the cell called BCR-CABL tyrosine kinase. And in the cancer, they developed a drug to block the overactivation of that enzyme already. Now, we have found that Parkinson's patients also have overactivation of that particular enzyme, leading to earlier death of brain cells in Parkinson's. And based on that, we propose that if we use the same drug that was used for chronic myeloid leukemia, targeting that enzyme, and slow down the enzyme in Parkinson's patient, maybe that will slow down Parkinson's disease. So phase 1 study was done in Georgetown and was very strongly positive. Now 2 phase 2 studies are going on, one at Georgetown and one a multi-center trial by Parkinson's study group that we are involved with or have been part of that. And that study is looking at now using that CML cancer drug with a known target, also active in Parkinson's patient, to slow down Parkinson's disease. Another study you've probably heard that we did at Nebraska Medicine was to look at using an immune system activator called leucine. Leucine is not specific to any disease, it just activates the immune system in general, and we wanted to see if we activate the immune system, if the right immune system will get activated and the right balance will happen, and that will slow down Parkinson. Phase 1 study was done to look at the safety of it, and it was found to be very safe. That's the data I'm reporting here. And then now a phase 2 study I think is underway or being designed to look at start collecting the evidence that it actually works, that if you just blast the immune system and make it overactive, that it somehow finds that the right activity starts and it starts slowing down the Parkinson's disease. Gene augmentation therapy. So that's a very interesting concept. So why do only some cells make dopamine in the brain? It's because they have the right gene to convert the food into dopamine, and they don't have the other cells don't have that gene. So one idea now is that although the dopamine cells are dying, there are still billions of cells available in the brain. Let's recruit some of the others to start making dopamine in place of the cells that have died. How do we do that? We need to send that gene to that cell, and the way to send it, the messenger that can take that gene, is a virus. A virus can go and infect the brain cells, and after infecting them, add a gene into their genome. Viruses have known to be doing it for a long time. That's how HIV happens, the human immune virus deficiency, the AIDS disease. So these viral vectors are now being created where they have this specific dopamine producing gene that is now injected into the brain so that the other cells get infected. They get this gene and they start making dopamine so that we don't have to give dopamine to the patient anymore. They don't have to take pills or tablets anymore. So there are actually 3 or 4 genes involved in 3 or 4 steps. So this first study was looking at just giving one particular gene that is the most important or key gene. And now another study, and that again phase 1b trial was done, 8 participants, showed to be successful, and there was increased dopamine production in the brain as picked up on the dopamine scan or DAT scan. And now another company is looking at packaging 3 genes, so all of the genes needed in the sequence to produce so that even more cells in the brain can make dopamine to replace the loss of dopamine producing cells. And that study is underway. These viruses have to be injected into the brain, and what was injected, it remained localized so far, that's what it shows, and then they can help get more cells recruited to make dopamine in place of the lost cells. 750,000. There was this project last year, that finished last year, where they took all the known drug chemicals active in human bodies, all the known, and that number is 750,000, and tested them on the cell models of Parkinson. So they tested every single drug available in the known science on Parkinson's cell models to see if it could be potentially useful for Parkinson's disease. So how many do you think they find that may help Parkinson's disease? They found 57. They found 57 drugs already available in the market for other conditions that may potentially improve Parkinson's disease by looking at these 48 gene markers. And of those 57, there is already suspicion reported for 17 of those drugs by individual researcher or individual clinicians who said, I think this drug might help slow down Parkinson's, just like Bumetanide that I mentioned earlier. Somebody reported in '94 that this may help. So 17 of those 57 have already been suspected by others. 57 are now further supported, including those 17, are supported by this cell testing to say that these may help Parkinson's, and those 57 target the 48 known genes associated with Parkinson's disease. So that project is finding a lot of interesting drug. This is the most interesting to me. As many of you might know, that Dr. Bertoni discovered that melanoma is the only cancer which has a higher incidence in Parkinson's than any other, than normal population, and no other cancer has, actually all other cancers have a lower incidence in Parkinson's disease except for melanoma. And it's interesting that one of the drugs used to treat melanoma, called Debra Venom, is one of those 57 drugs that was found to be a potential cure or treatment for slowing down Parkinson's disease. And maybe that's that link that melanoma is more active in Parkinson. They also found something in the green tea, in Japanese green tea, that is of useful outcome for improvement of Parkinson's disease. And that basically shows me the hope that we are now starting to understand what are the cellular mechanism changes in Parkinson's and developing drug targeting those mechanisms to really fix and cure Parkinson's disease. And this is remarkable in addition to what's already out there, just like Dr. Torres have already mentioned, that we have these newly approved therapies in Brecha and Duopa and the new types of DBS mechanisms that we have, new programming styles and therapies that we have, and they have these emerging therapies with the new drugs that are coming out. There is an endless innovation going on in Parkinson's disease, but the most exciting to me is the cellular mechanism-based drug development to change the face of Parkinson's disease treatment. Thank you so much.
Thank you, Dr. Bhatti. They will be delivering the lunch to your table, as we previously mentioned. If you have a gluten-free card or a vegetarian card, you would have gotten a colored card and registration if you registered for that. Make sure you give those cards to the people that are delivering your meals. Also, we're working on the room temperature. We know it is cold in here, and they have turned up the thermostat a couple of different times. I think they wanted to keep you all awake. So enjoy your lunch, and we will have an exercise group at 12:50 that you all can participate in.